Right, so this is a Maths 1M revision seminar and I'm going to start off by talking about logic and proofs, and I thought what I might do is also talk about proof by induction. Even though it's not in the same topic, it's still a type of proof, so it couldn't be a bad thing to talk about. I had a look at the practice exam that was provided to you in your My Uni course, and it did have a few questions on general logic and on proofs, and so it's a reasonable thing to talk about now, because the fact that their practice exam included some questions like that is an indication that they're probably going to include them in the real exam too. Those of you who are listening in the future, in 2016 and beyond, you'll have passed exam and you'll know for sure whether they're likely to include it. But this year, you guys are doing this new version of Maths 1M for the first time. My poor little guinea pigs, you. So all we have to go on is that practice exam. So we're going to assume that since Stuart has put a question about general logic in the practice exam, that he's really interested in you knowing about how to do that. Right. So if you look at the practice exam question, it goes something along the lines of, suppose there are some properties called upness and downness and blueness of natural numbers, and decide if the following arguments are valid. Okay? So one of the purposes of this question is for you to not decide whether the statements are true, but whether the flow of logic from one to the next is valid. Okay, so logic and proofs, mathematical logic, is you make statements about statements as opposed to statements about objects. So I'm going to write that down. Most maths make statements about objects. Okay, so you might make statements like, e.g. 2n plus 1 is an odd number, and the statement is about numbers. Or one on root 2 is a unit vector. Which is a statement about vectors. So you've got objects like vectors, or numbers, or points, or planes, or complex numbers, or equations, okay, and you make statements about them, and you say that they are, you say things about them. The problem is that mathematical logic, the objects that you're talking about are themselves statements about other things. And so it's like a meta-math. You're going, well, the objects under study are no longer actual objects like numbers and vectors, they are now statements. So that's what makes it so difficult to talk about. Makes statements about statements. Okay, so it's a meta kind of maths. So for example, we will say something like, e.g. Okay, the statement P implies Q is equivalent to the statement not Q implies not P, sorry. Right. So that is a statement about statements. P implies Q is equivalent to not Q implies not P. And so this here is a statement, and this here is a statement. And even the P itself is usually a statement too. It's what they call a proposition. So we're no longer really interested in the true or falseness of things, though sometimes we are. Mostly we're interested in whether the flow of logic from one thing to the next is valid. So the things that we're most interested in whether the flow of logic is valid. Okay, so we don't have to actually start with something that's true necessarily. Yes, so it's a bit like you saying, with your maths, is my working correct? As opposed to saying, is the answer correct? Okay, so even if you copied down the wrong question, but all your working was right, it would seem reasonable to give you marks for the working that you did, even though the question was wrong. And so it's a similar sort of idea here in mathematical logic. Even if your question is wrong, even if the statement you've got to begin with is wrong, you might make more statements about other things, and everything that you've said in between is okay. So it's almost like mathematicians giving themselves marks for correct working. Okay? And so that's what this logic and proofs thing is about. And in order for mathematicians to talk about how they can talk about maths, yes, that's right, they need names for the different kinds of logical flows, okay, logical connections between things, so that when they talk about proof, they can say, oh, well, we use the contrapositive, or the converse is true or not. And that converse is a thing that you do to a statement to make a new statement. So there you go, that's my general philosophical rambling for the beginning. And now I am going to talk about a couple of things. So we're going to now do things, instead of doing things like adding numbers or finding the angle between vectors or multiplying matrices, we're now going to perform actions upon statements. So things that you can do to statements to make new statements. So in the same way that you can add numbers to make new numbers, we can add statements to produce new statements. And one of the things that we can do is to produce the contrapositive. So the idea is that you have a statement something like P implies Q, where P is already some sort of statement and Q is some other sort of statement. This is a big multi-complex sentence that has different clauses in it. So, for example, if you're human, you have eyes, and being human is P and having eyes is Q, and the implies that symbol is the constructing the if-then bit of it. So this is a big statement, and we can create a new statement. I'll do an example with actual words. We can create a new statement from it. Not Q implies not P. Okay, that's the mathematical logic symbols version of it. And if you do it in words, you'll have to put the not in the correct place based on the grammar of English or whatever language you're writing in. But here it's English, of course. Different languages have different grammar constructions for how to do this. So if you're used to doing it in say, Italian or Chinese, it will be different to what it will be in English. So some examples. If you are human, then you have eyes. Okay, so this would be the P here. You are human, and you have eyes is the Q. And the if-then is what's created by this arrow symbol here. Okay, so I've put these two different statements together into one bigger statement, and this is the thing that I'm going to perform the contrapositive on. And so there's an action. In the same way as you can invert a matrix, you can perform the contrapositive. So the contrapositive says, so the original statement is if you're human then you have eyes. The contrapositive is the other way around and everything's reversed. So if you don't have eyes, you are not human. Now the question is not whether that statement makes any sense, whether either of the statements make sense. The question is that this is just an action that we can perform on a sentence to produce a new sentence. Okay? And note where the not happened. In English you can't say, if not you have eyes, then not you are human. You have to put the not in the appropriate spot for the grammar. But when you read this aloud, this would be not Q implies not P, which would be not you have eyes implies not you are human. So you can't read it aloud in the same order that you write it in the maths. And that's just something to do with the way that grammar works in maths and English, which is slightly different. So this is not P, not Q, and this is not P. So I'm going to, in another colour, I'm going to write that down. Must get some new coloured pencils one day. So this would be P, and this would be Q, and this would be not Q, and this would be not P. That's the contrapositive. Okay? So if you want one that's a bit more like maths, if n is even, then so is n squared. Okay? So we have two statements here. We have P, that n is even, and Q, so is n squared. Now technically that so is n squared can't stand alone as a statement in its own right because it makes because the so refers to the previous thing. So I'm going to have to divorce it from the so in order to do that. So I need to think of this as if n is even, then n squared is even. Okay, so that I can turn it into a statement that can stand alone by itself in order to reverse them. So the contrapositive so if not Q would be n squared is not even. So this is not Q. Then n is not even, and this is not P. Now, since not being even means being odd, I could rewrite this statement as if n squared is odd, then n is odd, and that's okay. So that's how the contrapositive works. It's more a grammar problem than anything else, okay? But mathematicians are really good at seeing the patterns in all sorts of things, including grammar. Right, so at the moment, the contrapositive is just something that you can do to a sentence. You can rearrange it and change, put knots everywhere. And I should point out one more example. If A is invertible, then det A is not 0. Okay, that's another math statement that one could make. It's about matrices. If you've never seen matrices, that's okay, because we can just use the English grammar. So this would be my P and this would be my Q. But note that the Q has already got a not in it. So when I do the not version of it, it will take the not away. So that was my Q, that was my P. So Q was that the determinant of A is not 0. And so when I do the opposite of that, when I negate that, it becomes the determinant of A is 0. It already had a not, so not means is. And this is not P. A is not invertible. So if A is invertible, then the determinant of A is not 0. The contrapositive of that is if the determinant is 0, then A is not invertible. So as I said, this is just an action that we can perform on sentences to produce new sentences. At the moment, we have made no statement about whether this is something that you're allowed to do in order to produce a new sentence which is still true. It's just something that you can do. Okay, it's just an action you can perform. Just like scalar multiplication is an action that one can perform on vectors. This is an action we can perform on sentences. But the important thing to note is that when you perform the contrapositive, then it maintains the truth of the original statement. So if the original statement was false, when you do the contrapositive, the new statement is still false. If the original statement was true, then when you do the contrapositive, the new statement is still true. And that's something important. So anytime you want to prove something, you could alternatively prove the contrapositive instead, and it would be coming to the same result. Okay, so whoop. The contrapositive of any statement is logically equivalent to the original statement. I should probably say that. Okay, and that's a really important thing to know. It means that when I attempt to prove that the square root of 2 is irrational, I can start talking about, in the middle of that proof, I'm going to have to use the fact that n squared being even means that n has to be even. But that's too hard to prove, so instead I will prove that if n isn't even, then n squared can't be either. And what I've done is I've proved the contrapositive instead, but since they're logically equivalent, it means the same thing. Okay, that's a big thing in maths. So that means that a flow of logic that turns a statement into its contrapositive is a valid flow of logic. We're allowed to do that, and that's okay. The next thing that one could do to a statement is the converse. So with the converse, it's something that we can do about a sentence, and it's always a similar sentence to what you have for the contrapositive. You start with P implies Q. The converse is Q implies P. Okay, but remember, we're not at the moment dealing with whether Q implies P, P implies Q are equivalent to each other. We're just talking about something that we could reasonably do to a sentence to create a new sentence. So creating the converse is something that we can do to a sentence in the same way as finding the inverse is something we can do to a matrix. And so, just as an example, I had one before. If you are human, then you have eyes. So here's my P. You are human. Here's my Q. You have eyes. The converse is if you have eyes, then you are human. You just switch them up, put them around the other way. This is Q, this is P. Now, this is just something that we've done to a sentence to create a new sentence. Okay, it's mathematical English, if you like. And so we can create a sentence that says this, but it says nothing about whether the new one is true or not. It's just something we've done to a sentence. And as it turns out, if the first one is true, well, technically the second one's not true. If you have eyes, you don't have to be human, because there's other things that have eyes as well. Okay? And so just because the original thing is true doesn't necessarily mean that the converse has to be true. The converse and the original statement and the converse are completely independent of each other. There is absolutely no reason why either of them has to be true at all. Okay, so if one's true, it doesn't mean the other's true. If one's false, it doesn't mean the other's false. There is absolutely no way of telling whether the converse is true or not, regardless of whether the original is true. So this is the next statement. Sorry, the converse is logically independent of the original statement. I might say from. So, we've got two actions that we can perform on sentences at the moment. We can perform the contrapositive, and we can perform the converse. And when you perform the contrapositive, it's a valid logical step. But when you perform the converse, it's a fallacy. You can't necessarily be absolutely certain that the converse is also true. And the reason we have words for these things is so that mathematicians can say something like, if the determinant of a matrix is 0, then the matrix is invertible, and the converse is also true. So instead of having to make the whole second statement, they can just say the converse to refer to the whole statement that they could have made. In the same way as I say, if a number x is even, then its triple is also even. I do not have to say 3 times x, I can just say the phrase, it's triple. So, and the determinant is a complex calculation, but since we have a name for it, we can talk about it without having to explicitly define how it's calculated. So that's how we're talking about language now. We're saying this sentence is true and the converse is also true, or this sentence is true but the converse is false. Okay? And so we can now use language to talk about language, which is called meta-language. So that's what meta means. It means self-referential. My favourite meta word is meta-affect, which means your feelings about your feelings. So similar to feeling guilty for feeling happy. When someone hurts themselves and you say feeling guilty for finding something funny, that's a meta feeling. So we're talking about meta language here. So these are things that we can do to sentences. We can actually just simply negate things. Okay, an ordinary statement that does not include an implies sign can be negated. You can just stick a not in it. I really should have done this first, but anyway. So negation is a process that you can perform on a sentence, and in English, sometimes you do it by adding a don't, sometimes you do it by adding a not, or removing a not if it's already got a not. So negation means creating the opposite, so everything else except that statement. Okay, so just as an example, the negative is I am not human. It could spell correctly. Okay, so I can create a negative on something. But there are some statements that are really quite complicated, and they have multiple pieces to them. And so you can construct statements out of other statements in the same way that you can construct sentences with different bits in it. You know, I am human is fine, but I could also say, you know, everybody is human. And that's saying that's a bit more of a complicated statement. And we want to know what the negative of those sorts of statements are. So every person is human. We want to know how to do the negative of that statement. What is the matching statement which is everything except that? Okay? I'm not trying to say one of them is true or false. I mean, obviously if one's true, the other has to be false because that's how negation works. But how do I construct the opposite of this statement? And the best way of thinking about it in terms of, is to think about it in terms of sets. There is a set of people, and they are all human. That's what this statement says. So in maths, this would say, for all people, the person is human. Okay, that's a maths sort of way of saying it. And you wouldn't even say people, you'd probably say person in maths. So every person is human is the same as saying for all persons, person is human. Okay, which is how you do it in maths. For all x, I'll do a maths one in a minute. Okay, and the opposite of that is not to say that every person is not human. That is not the opposite. Because there's a whole lot of possibilities that aren't included in either of those statements. Every person is human and every person is not human excludes all the possibilities where some people are human and some people aren't. And we've left them out. And so we need a way of dealing with that. And so the best way to test if you've done the negative properly is to see if there's a possibility that's not covered by the two. So the negative is, just to put us out of our misery, okay, so every person is human. The negative is not all people are human. Which is the same as saying, okay, which is the same as saying, there is at least one person, there is a person who is not human. Okay, to say not everybody is human is the same as saying here are all people who are, there's at least a couple of, one or at least one, maybe several, but there's at least one person who isn't. Okay, and together they cover everything. Now this is quite difficult because grammar in English is, and in most languages in terms of negatives, is quite ambiguous. Okay, so we have to be really specific when we talk about maths, and so now we have that the opposite of all is not all, which is not the same as all not. Yes, okay. So, and what that means is that we'll say, there exists a person with person not human. Okay, that's the mathsy way of saying it. So when mathematicians write this backwards E, it means there exists. So there exists a person where the person isn't human. So the opposite of for all people the person is human is there exists a person where the person is not human. So you'll see that when we did the minus, when we did the negative of a statement like this, the actual part of the statement, which was the bit that talked about the true or falseness, is here, and that got negated. We put a not in it. But the for all became a there exists. And it works the other way around. There exists a person, so there exists a person with no eyes. The opposite would be everybody has eyes. Okay, because if it's not true that there is a person with no eyes, then there must be someone, then that means everybody has eyes. And that's the idea behind it. So here's the math statement of it. You know, for all x in the natural numbers 2x plus 1 is e odd. Okay, that's a math statement. For all x in the natural numbers, 2x plus 1 is odd. And that happens to be true. And the negative of that is there exists an x in the natural numbers where 2x plus 1 is not odd. So what happened is that the for all became a there exists, and the is became an is not. And it works the other way around. If it's a there exists, it will become a for all. Now, personally, I do not find it's not usually a good idea in ordinary natural English to write a for all or a there exists sign. If you do maths for IT next semester, or follow on in some of the computer science courses, or even over in arts in the philosophy course, you may talk about formal logic systems where you will use these symbols quite heavily. Okay, so there's several courses around the university that use this, which is one of the reasons they've introduced it into Maths 1M. But even in natural language, the important thing to realise is that the opposite of everyone is not everyone. It's not everyone isn't. Okay, so just as a final example, so the opposite of everyone is here is not no one is here. They're not opposites. Okay? The opposite of everyone here is somebody's not here. That's the opposite. Okay? So the opposite of everyone is here is someone is not here. And so that's saying for all, and this is saying there is. This is saying for all people the people are here, and this is saying there is a person who isn't here. Okay, so this is a for all sort of statement, and this is a there exists sort of statement. It just takes some getting used to. And one I would like to, if you give me just a couple of minutes, I can come up with an example that the reason why this is important is that if you want to do the contrapositive, for example, of something that's really a complex sentence, you're going to need to take into account all of these ideas. But I'm trying to think of one at the moment, so give me a second. So if there is a prime number p such that 2 to the p plus 1 is prime, then so if there is a prime number p such that 2 to the p plus 1 is prime, then Fermat's theorem is false. That's a really complex statement. Okay? And it has two pieces. All of this is my p, and this is my q, and this is p implies q. Okay? There is a prime number p such that 2 to the p plus 1 is prime. That's my capital P. And Fermat's theorem is false. That's my capital Q. If I wanted to form the contrapositive of this statement, the contrapositive of this statement would be not Q implies not P. So let's see. Not Q. Fermat's theorem is false. Well, not Q would mean Fermat's theorem is true. And, okay, so if Fermat's theorem is true, then, so this is my not Q, then we need not P. Now let's see, P is, there is a prime number P such that 2 to the P plus 1 is prime. So the opposite of there is for all, is everything. So the opposite of there being a prime, so there is a prime number P such that blah 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 would mean the opposite would be every prime number has not that. Okay, so let's see. So there is a P such that blah blah blah, every prime number has not that. Okay, then every this is not P. Okay, there is a P became an every P, and the 2 to the P plus 1 is prime became a 2 to the P plus 1 is not prime. So you'll see that I'll use a different colour, the there is here became every, and the is prime became is not. So that's how that statement got negated. Right. It's a valiant effort by the School of Maths to attempt to teach people some of this language stuff, so that when you get to later on and you have people doing complex negations and contrapositives, it doesn't freak you out wholly. But it is a really difficult thing to learn. And it will take, if you go on in maths, you'll get used to it as you go along. But it's useful to know that you can just manipulate sentences, and at this level, this is all we're dealing with. So the final thing is just a second. Is an argument valid? Well, an argument is valid if the logic flows from one to the other. And that's pretty much all there is to it, except that we do have two rules that we've just learned about the validity of arguments. If the logic flows from a statement to its contrapositive, then that's a valid argument, because the contrapositive is equivalent. If the logic flows from a statement to its converse, then that's not a valid argument, because the converse is not necessarily doesn't necessarily match the original. And if the logic flows from a statement to its negative, then that's definitely false. That's definitely not valid, because the negative and the original are definitely not the same. So I should probably say that the negative of a statement is definitely not equivalent to the original. That's the whole point of the negative. It's the exact opposite. And so if the original's true, then the negative is false. If the original's false, then the negative is true. So this is our way of dealing with things. If something proceeds from an original to a negative, then the argument is invalid. Unless you're aiming for a contradiction, of course. But in one step, if you go from the original and you just switch it round to the negative, then you've done something wrong. If you go from the original to its contrapositive, then that's okay. And if you go from the original to its converse, then that's not a valid argument because you can't be sure. And that's really the only advice I have on that front, other than just looking at it and just thinking through whether each bit follows from the one before. Lewis Carroll, who wrote Alice in Wonderland, and Alice in Wonderland as a book has its 150th birthday this year. Lewis Carroll was really into logic. That was as a mathematician, that was one of his research areas. And it wouldn't be a bad thing if you were interested in this, maybe after the exam, to go and look up Lewis Carroll's writings on logic. And he used to do this game called syllogisms, where he would say things like, well, if all cats speak French and some chickens are cats, then logically that would mean that some chickens speak French. Okay, this is a valid, just as a valid argument. If all cats speak French and some chickens are cats, then logically it must be true that some chickens speak French. That's an example of direct reasoning. You don't need to... Remember that the whole purpose of this is just to look at the flow of logic. So we flowed from these two statements to this statement, and that's a perfectly legitimate flow of logic. Okay? Some chickens are cats, cool, the cats speak French, so since the chickens are cats, they speak French, cool, some chickens speak French. Sweet. Okay, that's the sort of thing that you're going to be expected to do in, well, at least it's in one of the exam questions. Only it's about numbers, so it sounds a little less frivolous. But one of the points that your lecturer made was that actually it's really a puzzle. Okay? And assessing whether this flow of logic is valid is the same style of thinking as assessing whether a real flow of logic in a real proof is valid. Okay. And the other thing I did want to talk about before I moved on to other topics was about proof by induction. In fact, I may stop the recording and start it again so that when you go looking for it, you can find the bit on induction in its own video. Before I move on, anyone got any questions about the logic bit at all? Or are you just reeling?